Okay, welcome. How about, woohoo. Woohoo! All right, good. Okay, I think it's better when it's on video, but okay. I think I need an editor. So last time we shared and sort of kept secrets, right? That was the idea last time, right? What we did is we showed how the idea was a polynomial. D plus 1 points determine a polynomial, right? You construct a polynomial of degree k. You're trying to share the secret among n people, where any k of them can reconstruct the secret. So it should be k minus 1. It should be k minus 1. But if you construct a polynomial of degree k minus 1 where the zero, the point, the value at 0 and the polynomial is the secret, or in other sense, a0, the lowest coefficient, is the secret, then you can give out any endpoints. Now, n can be as large as you want, right? As long as your field is big enough to support that range of points, and any k of them will reconstruct the secret. Okay, so we'll do coding theory, where we tolerate packet drops. Those are called erasure codes, and tolerate errors in packets, which is error correction. So really, erasure codes, we essentially already did it, right? That's what secret sharing is, right? In some sense. So let's just go quickly, but you should think, oh yeah, I know the answer already. The mathematics here is there's a big polynomial, and any set of d plus 1 points determines the polynomial. So stare at the above. Okay. Okay. What does it mean? Okay. It says there's many representations of a polynomial. Right? Many. Right? That's what it says. There any d set of d plus 1 points. So there's just so many representations, right? Like for a line, there's the coefficient representation of which there's exactly one, right? There's one coefficient representation, but many, many point value representations. So this gives you like a lot of options to represent the information that is in the coefficients of the polynomial, right? Any set of points that is large enough gives you complete information about the polynomial, right? About the coefficients. So there's you think of this coefficients AD through A0 as just information. There's many ways to represent that information. Have you seen that before? Have you seen the many ways to represent information? Right? You remember linear algebra? You could have all kinds of different bases to represent the same point, right? You had to decide which basis you were working in, and then this is exactly the same thing. All these other representations with different values are simply other bases for this information. Okay, for this, there's a d plus 1 dimensional space, and all these other things are just different representations of that d plus 1 representational space, actually in higher dimensions, in fact, right, where it's also redundant. Okay, so it's really, connected. It's a sort of a deep information thing. Okay, generally a D means that at most D. These are details. These are not a big deal. Arithmetic, if you get confused by at most D, just D or less. We're working when we do an arithmetic modulo P. We're working with numbers that are smaller, right? The representation of those numbers is smaller. Okay, so in some sense, if you're working log P, you're working P. Each one of these is a log P bit number. Okay, so the amount of information is D log P. Okay, so here's this picture. You lose 3 packets. This encoding scheme was to copy the packets, right? We have 2 copies of 1, 2 copies of 2, and 2 copies of 3. This encoding scheme is very easy because you just make 2 copies. But it has a problem, right? If you lose 3 packets, you only get packet 1, 1, and 3. You've lost the information in packet 2, right? Okay, so there's an N packet message and a channel that loses K packets. Even before you start, you need to you need to send N plus K packets, right? Because you're going to lose K of them, so the total amount of information in the packets is N, whatever amount of information you could pack into N packets. If you lose K of them, you have to, you have N left, right? If you send less than N plus K, you'll have fewer than N left, and you don't even have the information to reconstruct the original message. Okay, it's just an information theory argument, but when somebody says information theory arguments, it seems like it's intimidating. Really, it's just obvious. Information theory arguments are easy. That's what they are. It says if you have N bits of information, you can't represent that in less than N bits of information with less than N bits. That's the thing. Okay, that's what an information theory argument is. Okay, so any N packets should allow the reconstruction of of that whole N packet message, right? So it says, in some sense, whatever information was in that first N packet message, it must be kind of smeared out among the N plus K packets uniformly, right? Because any N of them are good enough, right? So a little bit of each packet's information in the original person must be sort of spread out through all the other packets, right? It's kind of a cool thing. Right? Okay, so any endpoint packets allow the reconstruction of a degree n minus 1 polynomial. This is exactly what we were discussing on the previous slide. Okay? Okay, so, I mean, they're syntactically related. Right? You can see that I lined them up so that it seems like, okay, well, the solution should be kind of obvious by changing the words. Right? It's just the same exact thing, almost. Okay, so you use polynomials. Any set of endpoints contain information about any set. Any should probably be emphasized. Contained information about about the n coefficients. The original thing we're trying to encode is the n coefficients, right? And so we're doing that. Okay. Or it also gives you information about all the other points. If you tell me what's the values anywhere else, I can tell you that too, right? If I reconstruct a polynomial, I can construct a polynomial, and then I can evaluate it at any other point. Okay? Okay, so the linear algebra view it's sort of representing the vector in a different basis. The basis elements here are the dot products of your coefficient vector with 1, x1, comma, x2 squared, comma, x3 squared. It's just a dot product. So you're simply representing it in a different basis. It's not orthonormal, but it's a basis. Okay? Does that make sense? Okay. Many bases, right? There's many bases. That's what this says. In some sense, this is a typical kind of basis. It's called a Vandermonde basis, but it's something deeper. If any of these words frighten you, that's okay. Don't worry about them. They're just supposed to be interesting. Okay. So here's a scheme, and it's just blindingly obvious now, right? A degree n minus 1 polynomial is determined by any n points. The erasure coding scheme is the following. You have the message, m0 through m1. I make through mn minus 1, right? There's n packets. I make them the coefficients of my polynomial modulo p. Now, p should be large enough where the number of bits that fit in each packet is about log p. Okay? And then you send all these points, and any k of them, any n of the n plus k packets gives you the polynomial, right? Okay, and it gives you the message. Now, in the notes, sometimes I think sometimes they encode the message as the values of the point at P1, P2, P3, P4. You can also do that. It doesn't matter, right? You can encode. You can decide that the values of the points on the first on the first n points on these n points is the value of your message, and then give them k more messages. The attractive thing about doing that way is a decoder doesn't need to do any work to reconstruct the polynomial. The decoder can just look at the values, the first n values, and if there's no loss. Okay. Okay, so this is the thing. You lose k packets. It's fine. Any n packets is enough. It's just the same statement, just with a picture that says satellite and GPS device instead of saying polynomial and points, right, at the end. Okay? So it's optimal. So this is beautiful, right? I mean, when something just works out perfectly, it's like, oh, nice, really nice, right? I mean, we're getting all the information that was in the original packet with no loss at all. So it's like perfect. Okay? Okay. So now we have a more complicated scheme. We have a more evil channel. Instead of just deleting packets, it goes inside the packets and changes them. Okay? So it's real evil, right? So not only now, if you knew which packets were changed, that's fine, no problem, right? You just throw them out and you do what you did before. You don't know which packets are changed. Okay? So here's the thing, here's the picture, and this would all be fine if I could say, get rid of B. And then there's at least 3 points. This is a 3-packet message. I had the right size polynomial, degree 2, and I can recover. But I don't know that B was corrupted. I don't know which one was corrupted, or if any were corrupted, right? That's the problem. Okay? Okay. So this is a Reed-Solomon code. Here, I'm doing the other encoding, just because either encoding is fine. Now I'm choosing a polynomial whose values are the message, for example. Okay? Does that make sense? I just changed the encoding scheme to be, instead of the coefficients of the polynomial, I'm saying it's a value of the polynomial at 1 is packet 1. The value of the polynomial at 2 is packet 2, and so on. Okay? So, which is the same. Yeah, I could have encoded the packets as coefficients, but I just wanted to show you the other way. It doesn't matter. We do both. Okay. Then what I do is, in addition to sending these first n packets, which are the real packets now, I send 2k more. Okay? So now it's weird, right? Because now the information about packet 1, 2, and 3, packet 1 doesn't contain any information about packet 2. It doesn't seem to, right? But somehow, so I'm not smearing out the information over all the packets. I'm just sort of smearing it out over the next 2k extra. The next 2k. I'm sort of packing the extra information into there somehow, right? This is what this system is doing. Okay? But okay, this is just a little bit of philosophy and stuff that's going on deeper. So that part, philosophy is, what does philosophy mean? It means you don't understand it. Okay, that's what philosophy means. So that it's okay if you don't understand that part. But I'm going to be very careful to show you what parts you should understand, right? Like, and it's clear in the book and in the notes as well, like property 1 and property 2. They highlighted that in bold. Yeah, understand that. Understand those proofs, right, of polynomials. Okay, and we'll tell you where it's interesting here. Okay, so what happens now, you sent these P1 through P of 1 through P of n plus k, 2k, which you can call packets or you can call points. Okay, and what you receive instead in the packets is whatever you receive, R1 through Rn plus 2k. Some of them are the same as original points or packets. Some of them are just different values. Somebody changed those values. K of them. Okay? Okay, so that's what happened. Okay? So this is all so here's the property. We know that for at least n plus k points, they do agree. P of I agrees with R of I. What you got is actually the real value of the polynomial evaluated at I. Okay, that's what P of I means, the real value of the polynomial evaluated at I. R of I is the thing you received. Okay, which may or may not be the real value. But for at least n plus k points, it is the real value. The correct value. Okay? P of x is a unique degree n minus 1 polynomial. That's just by construction, right? There's only one that hits those and points that are specified by the values of the packets. Okay, so now, but it's the only one that contains more than n plus k received points. Only the original one. Okay? Right? Is the original one consistent with n plus k received points? This is something you should understand. It's not philosophy. Right? We knew all n plus 2k points we sent were consistent with this p of x, and we made k of them inconsistent, so that says at least n plus k of them are consistent. Right? The errors could have only messed us up by k. Right? The original polynomial is consistent on all n plus 2k points, and this polynomial and the original polynomial, we've changed only k of those values for Ri, and so therefore p of x is consistent with all but k of those points, or at least n plus k points. So that's sort of obvious, but we need to argue it's a unique one. It's the only one that's consistent with at least n plus k points. Okay, so already from this property, you know how to reconstruct, right? Okay. Okay, so but let me just first of all I'm gonna tell you how to reconstruct again, but you should know how to reconstruct. How might you reconstruct here from these two properties? This property is true because we know it's true, and this property I'll prove in a moment. But from this, how can I find the original polynomial? It's not a very fast algorithm. It's maybe the dumbest algorithm possible. Yeah. Right. Does he say no offense, but that's the dumbest possible algorithm that works. That works is good enough, right? Like trying everything, it's a great algorithm because it always works, but it takes a lot of time. But he phrased it exactly correctly. He said, you just try every possible subset of n plus k points, you find a polynomial of degree n that is consistent with it. And how do you do that? You just pick any of those points, and you find a polynomial that you use interpolation and find a polynomial that's consistent with those n points, and then see if it also is consistent with the other k points. Right? Very good. Right? Does that make sense? These properties are enough to give you sort of a bad algorithm. It's not a bad algorithm. It works. It works for sure. Right? You will always reconstruct the correct polynomial. It just takes a lot of time because you're trying all subsets of points. Yeah. 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 What he's saying is what you can do is pick a subset of n points, find the polynomial that fits it, and just test it on the other two k points. And if you get one that fits at least those first n, right, because there's always a polynomial of degree n minus 1 that fits any n points, and we know how to reconstruct it efficiently, and then you just check it against the other k. So that's also fine. Okay. I think they're sort of equivalent. But. Okay, so let's prove this property. So the point is, I want to say this is unique. It's fairly clear. Properties P of I is equal to R of I for at least n plus k points because they only differ in k points, and there's n plus 2k, right? You subtract. Okay, P of x is a unique degree n minus 1 property that contains greater than this many received points. Okay? So 1 is true, it's only k corruptions. Okay, so now let's assume for the contrary, right? There's another polynomial that's different than p of x that has an degree n minus 1 and is consistent with n plus k points. Okay? So k of x agrees with r of I n plus k times. Okay? That's what I'm saying. It's just this polynomial fits almost all the points, all but k of them. Now, we know that p of x agrees with r of I n plus k times because there's only k corruptions, right? That's what property 1 says. Okay. So the total points. So now I'm going to count how many agreements are there total? Well, Q of x agrees with R of I n plus k times. P of x agrees with R of I n plus k times. So the total number of sort of agreements or points that are contained by both of the polynomials is 2n plus 2k. Right? I'm just adding it up. Okay? So I'm going to call those pigeons. There's p pigeons. Okay? Now, how many points can they agree on? So some of those points, both q of x and p of x will get right. Okay? That's what we're saying, right? Both q of x and p of x will, if they agree, if they both agree with say q of I equals R of I and p of I equals R of I, then q of I equals p of I for that value of I, right? If they both agree with the same received value. Okay? So the number of received values is n plus 2k. That's the number of places where they can agree. Right? Q of x and p of x. Okay? So that's the number of holes. Okay? So now if we put 2n plus 2k pigeons into n plus k hole, 2k holes, some of the pigeons have to go in the same hole. Is that correct? And at most 2 pigeons go in the same hole, one from qx and one from pi, because they're all different. All those pigeons go in different holes. Okay? So now we say, how many holes are there where there's 2 pigeons? That's what we're asking. Well, it's the number of pigeons then subtract the number of holes. So there's at least n holes where there's 2 pigeons. Okay? And now, what are those 2 pigeons? Well, pigeon 1 corresponds to polynomial 1, or q, or p, and pigeon 2 corresponds to polynomial, the other one. Okay? So that says, at these points, at these holes, they really correspond to received values. They call the received value is a value that qi agrees with this value, and p of I agrees with this value. For these 2 pigeons, being in this hole, it says that q of I, that's a point where q of I agrees with p of I. Okay? So now we have degree n minus 1 polynomials that agree at least n points. Okay? If these 2 polynomials agree at n points in the degree n minus 1, what must they be? The same polynomial. There's a unique polynomial of degree n minus 1 that goes through n points. Right? So that's the proof. Okay? It's just this, that's where it happens. Okay, this proof always gives, everybody's looking at me, what? Okay. I don't know whether this is helpful. It may make you be more confused, but I'm going to give you an example, okay? So you have a 3-packet message. So we're going to send n plus 2k, which is equal to 5 points. We're allowing 1 error, 1 corruption. Okay, you receive these 5 points, R1, R2, R3, R4, R5. One of them, you know that 4 of them are consistent with the original polynomial, but one of them is not. You don't know which one. Okay? So only one I where Q R of I is not equal to P of I. Okay? So P of X contains 4 of these points, R1 through R5. And now let's assume there's another degree 3 polynomial that contains 4 of these points. Okay, so then they must have 3 common points. Okay, since P of X contains 4, Q of X contains 4, there are only 5, so they agree on 8 minus 5, which is 3. Or pictorially, this is what it has to happen, right? So each of these holes, I should have maybe drawn a hole, but I was in a rush. So here's a hole, or point. Q of X is correct on this point, R1, and P of X is correct in this point, so they're both in the same hole. Here, only P of X is correct, right? Here, P of X and Q of X is correct, and here P of X and Q of X is correct. Here, only Q of X is correct. Okay? So that says that, well, you see 3 holes where both P and Q are correct, right? That's all and it's just a little bit of counting, right? There's not enough room for them all to be correct on different sets of points. Okay? Degree 3 means that if they are the same, it should be degree 2. That implies that P of x equals Q of x. 5 points on a degree 2 polynomial. Okay. Okay, so here's an example. Here's this Reed-Solomon code. Here I've encoded the message 306 as this polynomial, where now remember, in this case, for this encoding scheme, I'm encoding the polynomial, the points as the values on point 1, the value on point 2, and the value on point 3. Okay? So this is P of 1 is equal to 3, that's the first packet. P of 2 is equal to 0, that's the second packet, and P of 3 equals 6, which is the third packet. Okay? So this is an encoding, this is a valid encoding of this message, right? That if you evaluate the polynomial, let me just evaluate the polynomial for 1. If you plug in 1 into x squared plus x plus 1, you get 3, like you're supposed to. Right? Okay. So now you send these 3 points, which are just the message. Now you're just sending the message in some sense. And you're also sending 2 more points. So you're just evaluating this polynomial on 4. You're evaluating this which, say, if you put in 4 there, you get 16 plus 4 plus 1, which is 21. 21 mod 7 is 0. So P of 4 is 0. Okay? And you can do the same thing for P of 5. Okay. So this is nice because if you don't lose anything, if you know nothing was corrupted, I don't know how you know that, you just get the message back in the first 3 points. Okay. Okay, so now let's say we received this message we received this. So I'm allowed to corrupt 1 packet. The channel is allowed to only corrupt 1 packet. So I'm saying they're corrupting packet 2. And here's the corruption here. It changes that 0 to a 1. But we have no idea, right? We've only received 31603. We have no idea whether this is correct or not. We don't know where the packet was corrupted. We don't know that, right? So P of I equals R of I for n plus k points. I'm just sort of instantiating all the numbers, which is 3 plus 1, which is 4 points. Okay, and that's what we see. Right? The original polynomial, if you corrupt 1 and you sent 5, it means they agree on 4. This one agrees on 4. Okay? Okay. So now the slow solution is for each subset of n plus k points, you fit a degree n minus 1 polynomial q of x to n of them. I think your solution is actually faster, but I did the slower one. Fit degree n minus 1 polynomial q of x to n of them. We know how to do that. For any n points, we know how to fit the polynomial. We can use either Lagrange interpolation or this linear system. Okay? Either one will work. You check if it's consistent with k more. And if yes, you output q of x. Okay? So for a subset of n plus k points where r of I equals p of I, the method will reconstruct p of x. For any subset of n plus k points, there's a unique degree n minus 1 polynomial that fits n of them. That's what I used in the first step to say I can reconstruct a degree n minus 1 polynomial. And where q of x is consistent with n points, n plus k points, we have the second property. That means that polynomial is p of x. There's only one. Right? That was the argument we made in the previous slide. Okay? So it reconstructs p of x, and this procedure only reconstructs p of x. There's only one polynomial that will work for n plus k points. Okay? Okay, so here's an example. Here's p of x, which is something. It's some p2, p1, and p0, right? This is all we see on the receiving side. We don't know the polynomial now, right? That's why at the top of the slide is only the received words, right? So for us, all we know is that the polynomial is degree 2. Okay, so let's try to reconstruct it. We're going to just do the algorithm on the previous slide. Okay, so what we know is it's a polynomial of degree 2, and what we don't know is we don't know the coefficients of that polynomial. So we put variables in for them, p2, p1, and p0. Okay? Okay, so now we write down all these equations. Are all these equations accurate? Which one is not accurate? Yeah, I mean, we're supposing there's a polynomial that fits that satisfies these three. We're just plugging in all the values. First of all, let me just remind you how I got the equation. The first equation is I'm plugging in 1 into this p of x, and what comes out is p2 plus p1 plus p0. The second equation, I'm plugging in 2 into p of x, and I get p2 times x, 2 squared, which is a 4, p1 times x, which is 2, so I get 2p1, and so on. Okay, for the second line. Okay, so I just wrote down the equations in this way, and what the algorithms on the previous slide said, well, let me just guess which one's wrong, essentially. Let's assume this one's wrong and solve the rest of the equations. Is that going to work? Not necessarily, right? Because if you saw it, one of them is not right. Which one's not right? Okay? So there's no consistent solution. Now let's assume point 2 is wrong and solve. There's a consistent solution, and we're done. Does that make sense? Okay. So the way we solve, once we assume point 2 is wrong, we just pick any three of these equations. We solve for p2, p1, and p0, and then we check it against the fourth one. Okay? Okay, so this is the brute force way of doing it. Okay. Okay, so so in general, what happens is you get lots of equations, right? In general, you have whatever number of equations are appropriate for your n and your k. Okay? And there's the error, right? Somewhere in there. You don't know where the error is. Okay? It could be anywhere, right? Like you see, maybe it's there, maybe it's there. See, it's moving around. We have no idea. Oh my. So what we do is we try everywhere, right? But if there's k of these, there's n plus 2k choose k possibilities of where the errors are. So this is a big number. Okay? It's something like n over k to the k. It's exponential in k. So if you have 5 errors, you're going to get n to the 5th or something, right? Or if you have 100 errors, you're going to get n to the 100, which is a disaster. Okay? So how do we find where the bad packets are efficiently? That's the question. Okay? So, yeah. Okay, so, where has my little dog gone? Where can he be? With his ears cut short and his tail cut long. Where can he be? Peter probably wouldn't like this with the cut parts of the ears and the tails. It's sort of like, oops, sorry. Where have my packets gone? Wrong. Where do they not fit? With the polynomial well put, but the channel a bit wrong. Where do we look? Does put rhyme with look? I don't know. Who wrote this? It's really a compelling question. Okay, maybe that's not compelling, but the question is compelling, right? Like, how do you figure out where these are, right? Where's the structure here? Okay, so where? I mean, you're just given this. You have these equations. You don't know which one's right and which one's wrong, right? Okay, so here's the trick. So we're going to multiply the equation I by 0 if and only if P of I is not equal to R of I. In the very first lecture, I said multiplying an equation by 0, if you say 3 equals 4, is that a correct equation? Is 3 equals 4 a correct equation? No. But what if I multiply both sides by 0? What do I get? 0 times 3, which is 0, and 0 times 4, which is 0, and I get 0 equals 0. Now is it a correct equation? I mean, it's really, really stupid, but it is correct, right? It's like an obviously wrong thing to do in some sense, right? to take a bad equation and make it right by multiplying both sides of it by 0. That's what we're going to do. Okay? No. See? Everything's good. I have n plus 2k equations. They're all good. Right? It's like, oh my God. Okay, so that's good. Oh, but the whole question is, which equation do I multiply by 0? If I knew which equation to multiply by 0, I could just throw the thing out. Right? I don't need to this is stupid, right? Yeah, which equations do I multiply? See, I mean, it's really a question. Okay, well, what's the answer? The answer, of course, is a polynomial. We're going to use a polynomial, right? Okay. Well, wait, we don't know the polynomial, but we can find it, right? We've already been in situations where we don't know a polynomial, but we know the point values on the polynomial, and we can find it. So there's something here that we've been using as a theme, and this is, let's say, we assume we don't know where the errors are. So what do we do when we don't know what something is? We write variable names for them. Okay? So let's write the variable names for the things we don't know. We don't know the points on which we made the mistake. So let's say we made a mistake at point E1, at point E2, and at point E3, and on to E sub k. Okay? So that's what we're going to assume. We don't know where the errors are. We're going to write variables for them. Okay? And now, in the example above, in this example above, I showed you where the error was. It's at 2. So in that example above, it's the polynomial evaluated at 2, or R of 2. So the error is at the point 2, right? E1 is 2. Okay? So now the error locator polynomial, what property should it have? It should be 0 where the errors are. Now, if I have a polynomial x, I'm going to call it the error locator polynomial, and I'm going to make it be 0 where the errors are. Okay? And is this going to be 0 at E1? Is this, if I plug in 1, or E1 into here, will I get 0? Yeah, I get E1 minus E1, which is 0. Right? And I can keep doing this. This object, whatever it is 0 at all the values where there's an error. I don't know where those values are, right? But if I knew the right values for E1 through E2, this object does give me a 0 at the errors. Okay? What should I do with this object then? Is it non-zero at the places where I don't have errors? Right. Okay, so that's the other thing. If you multiply two numbers together and both of them are non-zero, what is the number? Is it non-zero? Yes, in a field. Okay? So it's non-zero. It's only 0 where the errors are. Okay? And it's non-zero where the errors aren't. Okay, so now the flip side is if you have an equation that's satisfied and you multiply both sides by the same non-zero number, will it still be satisfied? Okay? So E of I is 0 if and only if Ej is equal to I for some j. Right? That's what it says. We know if, when is this value 0? When you plug into I, if it equals one of these numbers, one of these roots, essentially, it will be 0. And if it doesn't equal one of those numbers, it will be non-zero. So what do? We want to multiply the bad ones by 0 and the good ones by non-zero, right? And that's what we do. Okay? So, now we have this new system. Right? Okay? And in the above equation, E of x is x minus 2. We don't know that yet. We don't know the value 2. We still haven't done anything yet. Right? I've just introduced more variables, E1 through EK, and I said, well, here's this other set of equations that can hold. That can hold if I know the values Pn through P0 and E1 through Ek, then it will exactly specify the correct values for those will give me a solution to these equations. Okay? You tell me where the errors are, you tell me the polynomial, you plug it in, all the equations will be satisfied. Okay? Right? I mean, this is like, this is bizarre, but okay. Okay, but, okay, so here's an example. If you do this, the error locator polynomial is x minus 2. Voila, right? Now I just plugged in x minus 2, and then I use the value for 2, and I have this equation. Now all the equations are satisfied, right? This one wasn't satisfied before, but I've multiplied both sides by 0. So it is satisfied. So now I have n plus 2k equations that are satisfied. Okay, but I don't know the error polynomial. But I do know the form. So it looks like that. Now I have a system of equations, and how many unknowns do I have here? I don't know P2, I don't know P1, and I don't know P0, right? And I don't know E. So I don't know there's 4 variables that I don't know. And there's some constraints there's 5 constraints, right? Okay? 4 unknowns and 5 equations. One problem here is now they're nonlinear. Do you see why they're nonlinear? What does this do? You get an E times a P1, an E times a P2, and so on, right? So now you have equations that are no longer linear. And we don't really know how to solve such things, right? This is where our knowledge ran out, K through 12, and it's run out all the way to me. Maybe somebody knows how to solve these things. Okay. Nonlinear equation. Okay? Okay. Good. Okay, so let me, yeah. Yeah, so it's just the notation for the function, right? That you multiply by E, right? But for equation, what I mean, at least in this slide, in general, it just means a function. But what I mean in this slide is that for equation 1, I plug in E of 1 and multiply both sides of it by E of 1.
Okay, so in general, that just means a function?
E, yeah, the C dot in the middle, yeah. Okay. Okay, so good. So so that's where we are. We have this, n plus 2k satisfied equations, n plus k unknowns, but they're nonlinear. Okay? Okay, so I'll give you a break now, and then we can come back. Okay, so this is the equation. So again, remember these error locator polynomials have all these variables in them, right? It's some degree. What's the degree of the error locator polynomial? K. So that corresponds to K. It corresponds, normally it would correspond to K plus 1 unknowns, but it happens to be only K unknowns because the leading coefficient is 1. You might as well assume that, right? You can just divide out the leading coefficient because you just care about whether it's 0 or not. So, but they're nonlinear. And again, you can't see it in this picture, but you see it in this picture. When you have a variable here, the unknowns are the E, and the P0, P1, and P2. And they multiply each other here, right? E times P2. Right? That's not linear, right? It's non-linear in the variables. Okay? Okay, so now what you do is let's think about this. The thing that's really nice about polynomials is when you multiply two polynomials, what do you get? A polynomial. When you multiply a polynomial of degree 1 by 5 by a polynomial of degree 6, what do you get? Yeah, a polynomial of degree 11, right? Does that make sense? So really, you can think of this whole thing over here on one side. This is just a polynomial, right? In some sense, e of x is just a polynomial, and everything is linear over here. This is not an unknown, it's a number, right? But these are all unknowns, and there's some unknowns in here, and you're like multiply them together, and now you get quadratics of unknowns, right? But if you think of all of it as one, it's just a polynomial, right? E of x times p of x is just a polynomial, right? Q of x, the polynomial we're thinking about on the left-hand side, is just e of x times p of x, right? Okay, so now, what is the degree of p of x? It's n minus 1. What's the degree of e of x? It's k. So what's the degree of the resulting polynomial? It's n minus 1 plus k, right? So in some sense, this e of x times p of x is just another polynomial that we don't know. It's yet another thing we don't know. There's so much we don't know. But we have the information here. Okay? Okay, so what we know, we take that polynomial p of x and we take to multiply by e of x is just to think about it. We're just trying to think about it this way. And then what we get is a polynomial. And what we know about a polynomial is you can write down the coefficients. Okay, and you write down all the coefficients, a sub n plus k minus 1, that's the highest degree coefficient, all the way down to a0. Some set of coefficients. I don't know what they are, right? I don't even know their relationship to the coefficients of p and e. It's like it's too hard for me. But it has something. You know there's coefficients there, right? Okay. I mean, this is genius, right? It's genius. It's just a polynomial, okay? So now what you have is equations. Each one of the equation is an equation of this form. There's another polynomial. The left-hand side is exactly e of x times p of x, which is q of x, which is a polynomial. And we have q of I here, right? Okay? And then we have this other equation that it equals the received word or received value, which this is just a number, times a polynomial here. Okay? What's the degree of this polynomial? K. Okay? So how many unknowns are here? K plus 1 normally, but we're going to assume the highest degree A0, or the highest degree coefficient is 1, so there's only K unknowns. What about this? How many unknowns are in the specification of Q of X? N plus K, right? N plus K minus, it would be N plus K minus 1, but you also have A0. So N plus K. Okay? So this is the left-hand side. It's some polynomial. It's Q of X. It's exactly what we're saying it is here, right? E of X. We're plugging in E of I into E of X. This is all just for analysis, just to come up with our algorithm. We're plugging in I here for E of I times P of I, right? There's the I plugged into P of X. But now we're going to say, well, I'm not going to think about that form of it. I'm just going to think about trying to reconstruct this polynomial, which is the product. Okay? And this side is just r of I times e of I, right? So that's just one of the equations. I'm just showing you how they're all related, right? So up there we wrote it as e of x times p of x, but then we're noticing that it's just one polynomial. We might as well think of it as one polynomial, or we can think of it as one polynomial. Q of x. E of x times p of x is one polynomial, it's q of x. Okay? Now, all these equations, if you start plugging in, instead of thinking of it up there, if you plug in I here, you're going to have a sub n plus k minus 1 times I to the n plus k minus 1. So, and then on this side, you'll have the coefficients of e of x. Okay? Okay. So, e of x has degree k. So it looks like that. Okay, so there's k coefficients. There's technically k plus 1 coefficients, but we're just going to go ahead and assume the first coefficient in our error polynomial is 1. Okay? So there's k unknown coefficients in the error polynomial. And the reason I'm using b here is so as not to confuse you with the e sub i's. The e sub i's are where the errors are. The b sub k's is the other representation of polynomials where you write them as the product and just the coefficients. Okay? So the leading coefficient is 1. Why not? Because we only care about where the zeros are. Okay? So p of x, now you have q of x is equal to p of x times e of x. Now that has degree n plus k minus 1. So it looks like that. Right? So there's n plus k unknown coefficients. So the number of unknown coefficients is n plus 2k. Now let's see how many equations we have. We have n plus 2k linear equations, right? We have an equation like this. What I'm doing in this equation is I'm plugging in 1 into the formulas, right? I'm saying a times n plus k minus 1 times 1 to the 1, which is 1, and so on. That's what I'm getting on the left-hand side. On the right-hand side, I'm plugging in 1 into the evaluation of e of 1. And that's just going to give me this expression, which is an expression in terms of a bunch of variables. And then we'll get that. Yeah. Well, I'll show you. Okay. So do you see how I get them? Okay? Those are all the equations. So here, I'm just plugging in 2. I'm evaluating q of I on 2, q of 2. I don't know q of I, right? But I know I'll get an expression that looks like this because I don't know these values. When I evaluate 2 of I, it's really just to get this expression. And this expression, is it linear in the a sub i's? Okay. How about this expression? Is it linear in the b sub j's? Yes. So both sides of the equations are linear in all the unknowns. Okay? And so on. There's nothing, this to the k throws people off, but m is just a number, right? And it's just a value. So when you do this actual process, you're getting a 0.5, and you're plugging in 5 to this value, and you get some other number mod p. Okay? So you have n plus 2 k unknown coefficients of q of x and e of x, right? So now you can solve, right? Okay. And now do you want to find p of x? You just divide. You use polynomial division again. Okay? That's the algorithm. Are there questions here? Yeah. Right. So let's just count the coefficients here. There's n plus k coefficients here, and there's k coefficients here. So that's n plus k plus k. In the error polynomial, yeah. So this one, the coefficients here is this many unknowns, and the error polynomial has k unknowns. So what we're trying to do is we're trying to recover both the error polynomial and this product polynomial, P of x times Q of x. So the unknowns have to do with not knowing the error polynomial and not knowing the original polynomial. Okay? And the not knowing that would only give you n plus k unknowns, but the fact is what we're going to do is we're going to make it a little simpler and throw up the number of unknowns in the Q of x, right? We're going to say, well, okay, we're going to just treat that as n plus k unknowns. Okay? And that made it all linear. Okay, so this is it. Oh yeah, look at this. I'm super excited. That's me being excited. I'm like a chameleon changing colors because I'm so excited. Okay, so, right? This is shocking. Really. Hell, yeah. Yeah. Yes. Yeah, it's optimal. He's asked, is this also optimal? Yeah, because you have to know where you're getting two kinds of information. He's asking what's the information theory as to why you can't do better. Right? That's sort of what you're saying. Clearly, if you the basic information theory, the basic tentative information theory is that if you get n packets, if you want n packets of information, you better receive n packets. That's the base. That's all it is. Okay. So now, what happens with the channel? If you get n plus 2k packets sent in, right, and then k of them are corrupted, right? So some number of them are corrupted. And then you reconstruct. What do we learn? We learn the original n packets, and we also learn where the packets were corrupted. That's actual information. Okay? So the channel added information by deciding where the packets were corrupted. Right? And so we learn both of those things. So we learn the original n packets of information, and we learn these k other things about where they were corrupted. So we learn about n plus k things, so we better have n plus k total information. I mean, if you got that, great. If you didn't, that's okay. It's just sort of we'll talk about it. We will refer to these kinds of arguments a little bit in discussion. Okay, so here's an example. So here's our polynomial. So we're going to say our original polynomial was only of degree 2. We're assuming, this is our example where we're assuming we want to send 3 packets of information, and we're going to get 1 packet of corruption. So we're sending 5 packets total. Okay, so there's the error polynomial is of degree 1. Okay? So we get the error polynomial looks like that, which is x minus b0, right? So again, if you count the number of unknowns there are 5, right? And now we get 5 equations. And these 5 equations are really remarkable, right? One of them is trash. One of the equations is trash. But somehow that's fine. We like it. We're going to use it. It used to be trash, but we multiplied both sides by 0 somehow. And now it's not trash. Now it's actually helping us. Who would have thought, right? I mean, we abstractly are multiplying by 0, and we're getting information out of this extra thing, right? It's shocking. Okay, so this is the received word. This one is the one that's wrong. This one is trash, right? But it's okay, because if I know eventually I'm going to solve for this b0, and this b0 will plug in here and become a 0, and then the properties of all the a's will make this also evaluate to 0. That's the miracle here, right? So if you plug that in, you get this polynomial, right, which is some nasty polynomial, and then e of x is equal to x minus 2. It takes a while, but you can solve these equations, and then after you do that, what do you need to do to finish your algorithm? Is what do you do now to figure out p of x? We want to find p of x. What do we do? Yeah, we divide. Oh yeah, flashbacks. Voila. That's our original polynomial, right? X squared plus x plus 1. I mean, you have to trust me a little bit that the calculations in the middle are right. But you see, I did it, right? Just linear equation solving. And that's the original message. Remember, the received word I got was 1 here, right? But through this process, I figured out the original polynomial. Okay. Okay, so now one problem is this, right? Okay, so what is x minus 2 over x minus 2? You remember that? And like, what would they call that? A whole? Is that what they called it? A whole? There's something weird when you're dividing, right? Like here we divided polynomials and it all worked out. But, sort of dividing x minus 2 by x minus 2 is a slightly odd thing, right? So I went a little fast and loose here to say on whether this is actually always going to work. Okay, so one has to check these things because something can go kind of wrong when you're dividing 0 by 0, right? That you have to be careful. Anything can happen. Okay? Is it 1? It's 1, it's up there, right? It does something strange at 0. Okay, so this whole dividing by polynomial is a little subtle. So you have to be a little careful, right? At the last step, we divided q of x by e of x. But we know at certain points, e of x is 0, right? And we hope at the same points, p of x is also 0. So we have to make sure that this sort of operation works. Okay? It's a whole or something. Okay, so this is the error correction, and I haven't argued it. I I mostly argued it. I said there's n plus 2k equations and n plus 2k unknowns. But that's not enough, right? They may not have solutions, there may be multiple solutions, and so on. We have to deal with that. We still have to deal with all those issues from linear algebra that we had to deal with before. Okay, so you have a error locator polynomial, and that's telling you where your packets have gone wrong, right? You can factor, you can check all the values. So there's only n plus 2k values, right? So you just see where it's 0. So if you want to figure out the polynomial, where are the errors, you just evaluate the polynomial. And then where it's 0 is where the errors are, right? For example. Okay, Okay. Is there one and only one polynomial that you could, eventually you want to, when I did it, I reconstructed p of x. Now, is that always going to be the case? Right? It gives you something, gives you n plus 2k equations and n plus 2k unknowns. But I still haven't fully argued that there will be a solution and there will be only one solution. Okay? Okay, so there is a p of x and an e of x that satisfies the equation. Why is there a solution? Well, I constructed the solution, right? When I constructed the equations, I just said, look, if there's only k errors, I can construct an error locator polynomial. And I know the original solution, p of x. I constructed it, right? I did it from the beginning. I said I knew the original solution was p of x. I knew there's this e of x. I know what it is. And then I can construct a solution, knowing everything. So I know there is a solution to this set of n plus 2k equations. Is that clear? It's just the original p of x times the error polynomial where I define it as x minus 2 times x minus 3 if I know where the errors are. Okay? To prove existence, you just need to show there is one solution, and that's the solution. Okay? So the existence is easy. So it does exist a solution to the n plus 2k equations that works. But there might be many solutions. Like, for example, you already know there could be many solutions because it could be the case that there were no errors. In that case, just the original polynomial would work. And then you can just make up an error polynomial and zero out whichever equations you want, and there's lots of solutions to that. So in fact, there are multiple solutions typically. If there's fewer than k errors, there's going to be lots of solutions, in fact, to the set of the linear system. Okay? But what we want to say is that when we do the division, whatever solutions we have for this linear system, whichever one I get, when I do the division, I get p of x back. That's what I want to say. Because I didn't just try to compute q of x and e of x. There could be many that satisfy the equations. But when I divide, I better only get back my original polynomial. Okay? Okay. So here's the proof. We claim this. Okay? Q prime of x times e of x. I'm just doing, if you get rid of the p of x, I'm cross-multiplying. Right? That's where it comes from. Okay? So, but let's just assume this is true. I'm not going to prove it. Okay? Yet. Okay? Okay, but I'm going to use the fact that equation 2 implies equation 1. Okay? So, q prime of x times e of x and q of x and e prime of x are degree n plus 2k minus 1, right? Q of x was n plus k minus 1. E of x was degree k. So you add n plus k minus 1 plus k, which is n plus 2k minus 1. Now, if they agree on n plus 2k points, so they agree on n plus 2k points. We know they agree on n plus 2k points because that's what we're assuming, this claim. Now, e of x and e prime of x have at most k zeros each, right? Is that correct? Because why? The e of x and e prime of x are degree k polynomials, and any degree k polynomial has at most k roots. Any degree d polynomial has property 2 or property 1. Okay? Any degree d polynomial has at most k roots, so each one of these have k roots. These are completely different, right? There's just two solutions that popped out of my linear equations. But we know that the error polynomials, whatever they are, whatever they look like, have at most k zeros each. Okay, so we can now say these things are equal at n plus 2k points. The products are the same because they agree on n plus 2k points. So these polynomials here are the same, right? They have the same values everywhere because they're degree n plus 2k minus 1. So we can cross-divide at n points. Now we can't write this expression. We can't plug in values into this expression where e prime of x, e prime of I is 0. We're not allowed to divide by 0, right? We're not allowed to divide by 0 here either. But for how many points are there where this is not 0 and this is not 0? Well, there's n plus 2k points total, and there's at most k zeros for e of x, and at most k zeros for e prime of x, right? So there's n plus 2k minus the k for e of x and minus the k for e prime of x. So that says there's at least n places where you can do this cross-divide. Okay? For at least n points, you can plug in I here and not get a 0 here and not get a 0 in the bottom. And when you cross-divide, you have that these are the same polynomial at n plus 2k points. For all but 2k of them, you can cross-divide. Right? You can divide this side by e prime. You can divide both sides by e prime and both sides by e of x, and you get this expression. And you haven't divided by 0, right? This x minus 2. You did not divide by 0. That's not legal. Right? So you know that this expression is equal on n points. So if this expression is equal on n points, what polynomial are you going to get of degree n minus 1? There's a unique polynomial. So there's a unique polynomial that corresponds to, right? Whatever polynomial you get from this division process here and the division process here, those two polynomials are equal on n points and are of degree n minus 1, so they must be the same polynomial. Okay? That's the proof there. Okay, so we proved the theorem except for now we need to prove this theorem. We said that once we start with 2, we can then say that, well, whatever solutions I get out of this thing, when I divide, I'm going to get p of x back when I do the final division of the polynomial division. Okay, but I need to prove this statement, n plus 2k values. And here, obviously, what does the n plus 2k come from? The number of equations, right? It has to do with the fact that there's both solutions of the set of n plus 2k equations. Okay? So let's look. So here's the fact I'm trying to prove, that this cross, this weird thing is satisfied at n plus 2k values of x. Okay, so what we know is they're both solutions to all the equations. Q of I is equal to R of I times E of I, and q prime of I equals r of I times e prime of I. Okay? So now you know it's true for all these values. That's n plus 2k values, right? Okay, so now let's think about the cases. What if ei is 0 in this first line, if ei is 0, and that's, say, non-zero, let's just assume it's non-zero, then, well, even if it's not, it doesn't matter. If ei is 0, what is q of I? What is q of I? 0, right? Does that make sense? If there's a 0 on the right-hand side, the only value here can be 0. Okay? And the same thing here. If e of I prime is 0, then q of I prime is 0. Okay? So this is true, right? If e of I is 0, then q of I is 0. So this equation is true. At all places where e of I is 0, q of I is 0, so this equation is true. Well, we're trying to say this equation is true. Okay? And if e prime is 0, e prime of I is 0, q prime of I is 0, so this equation is true. So whenever e of I or e prime of I are 0, then the equation is true. Okay? Okay. So when e prime of I and e of I are not 0, then what can we do with this equation? Can we divide? Can we say e of I is equal to q of I over e of I? Can we say r of I is equal to q prime of I over e prime of I? Right? We can divide. Wherever e prime of I or e of I is not 0, we could just divide these equations and get this expression. They're both equal to r of I and they're equal to each other. And now, if I want to get back this expression, then I cross multiply. Right? And that's the proof. Okay? Okay, so points to polynomials, you just have to, the reason there's this subtlety is we have to deal with the zeros, right? You can't just divide things and expect them to work out, right? If you have a point value that's 0 and another point value, you can't just divide. So you have to argue a little carefully here. So that's what's going on. Okay? Okay, so there's a lot of stuff, but let me tell you the ideas. Okay, there's more stuff. Okay, but there's more stuff. But let me tell you the ideas. This is the idea, right? Any d plus 1 points correspond to 1 degree d polynomial. Any d plus 1 points give you back the polynomial. Can give out way more points. You can give out way more points, and if you collect back up d plus 1 points, awesome. Okay, so you could recover information. That's what erasure coding is doing. So that's what secret sharing is doing. Now for corruptions. What's the idea in corruption? What is the idea? What makes all this work? Okay, we send more information. We have to send more information because now you have to figure out where the corruptions are, right? That's this information theory. K errors, n plus k are correct. There's only one degree, so we made 2 arguments here. I'm just reviewing what arguments we made so you understand what was done, okay? And only 1 degree n minus 1 polynomial is consistent with k plus n plus k points, right? And that uses the pigeonhole principle, okay, to say any 2 polynomials must overlap an n, okay? Okay, now the efficiency is how do we actually decode this thing? Is we understand that we can fix k bad equations with a polynomial of degree k. Okay, that's the idea. Okay? So, and then the second idea is a polynomial times a polynomial is a polynomial. Okay? So you recover this instead. I mean, I gotta say, people in our field, when you say Welsh-Berlekamp, they're like, wow, that's beautiful. And it really is. So on that, I'll leave it. Okay? Thanks.
Two stages. First, showing that q times e prime is equal to q prime times e